really great to be here and see many old faces and new faces, and to mingle with mathematicians. And I have to say that I'm a physicist. I'm not a mathematician. I'm trying to understand some math, and this work is partially trying to a demonstration of our effort, trying to understand math. And my hope is that through this conversation, through this effort, it will help me to learn what it means, and also from a more physics perspective. Okay, and in particular, we're trying to understand the math behind topological defects. Is actually related to what Sakura was talking about in the morning from a more math perspective about all these non-invertible symmetries and defects and the higher category structure that they form. But my problem is that I don't use mathematical notations, and I'll try to understand things from a more lattice model perspective, and that's where we came up with this idea of so-called sequential quantum circuit. And so this is another connection that I can make to the talk in the morning. Joanne was talking about QCA and some other so-called finite depth quantum circuit. So the sequential quantum circuit is, in a sense, beyond finite depth quantum circuit. It's not finite depth, so it's slightly more powerful. But we put the word sequential. We put the word sequential in front of it because we still want to restrict its power to some extent. So I'll talk about what that is and how that is related to our effort in order to understand all these non-invertible, invertible defects. Okay, so the picture here is showing a cat. And this is the famous Cheshire cat. So this is a character in Alice in Wonderland. And I put the picture here because the name Cheshire is going to show up. People use this name to describe actually a very special kind of defect, which is the charge condensate. Okay, so let me get into the details of what it is. So before I do all of that, let me acknowledge all my brilliant collaborators. Nat is here. Maybe just Nat is here. And we have two papers already. One is about sequential quantum circuit as a way to map between gap phases. So one-dimensional, two-dimensional, three-dimensional gap phases, anything with a gap, we use sequential circuit to map between them. And the second one is more related to the topic of this talk, which is to use sequential circuit as a way to generate non-trivial defects, in particular Cheshire strings and other kinds of defects in topological phases. So this is with just Nat and me. Okay, so let me give you a little bit background of where this is all coming from. So I understand that this is supposed to be a conference about quantum error correction. So the connection to that is that there are these wonderful understanding that 2 plus 1D topological orders, and especially some simple examples of that, can be used as quantum error correction codes. And to characterize such topological order, we have understood that there is some very important data that we need to give in order to describe what kind of order it is. For example, what kind of anyon the system has, and how do the anyons fuse? What's the fusion rule? And how do they exchange and braid with each other? There's exchange and braiding statistics. This is a braiding process. And then put all together, supposedly, mathematically, this forms something called a braided fusion category. So this is just a big word I learned from math. And but my understanding is that mathematically, this is pretty well understood structure. So starting from objects, and then there's fusion, and then there's statistics, there's a very nice structure, understood structure in terms of this braided fusion category. And the everybody's favorite model, the simplest model, is the 2+1D Toric code. This is also most popularly used as a quantum error correction code, where we can consider a two-dimensional square lattice, and the Hamiltonian will involve some plaquette term of sigma x and some vertex term of sigma z. So this is the standard form of a Toric code. And we know that we can generate pairs of anyons. One is so-called the M type of anyon, and the other is the E type of anyon using string operators, just like that. So, yeah. And for Toric code, we know that there are three types of non-trivial anyons, and their fusion rule is like this, and their statistics is like that. The E and M are bosons, their composite is a fermion, and there's some mutual pi statistics. And finally, to completely describe the braided fusion category structure, we also need the associator, which is so-called the F move, to map between fusion sequences, different fusion sequence. Okay. So then the question is, what about 3+1D? And in 3+1D, we have quite some understanding already, and for quite a while I thought we understood everything. Because there are some very simple models from which we can see that, for example, 3+1D Toric code, or some simple gauge theory, where we can see that there are also point excitations. Although here in 3+1D, the point excitations cannot have arbitrary topological spin. It can be either boson or fermion. There's no anyon anymore. It's either boson or fermion. And other than that, there can be a flux loop excitation. So it's a loop-like excitation carries usually the gauge flux of the gauge field. And then, yeah, the charge can be either a boson or fermion. And then when you braid a charge around the flux loop, when they go around each other like that, when they go around each other like that, there's a Aharonov-Bohm effect giving you the corresponding statistics. So that's the simplest version of the story that there can be. So this is, of course, very simply embodied by the 3+1D Toric code, which is a generalization of the 2+1D version, where we have it on a cubic lattice. And now we have Hamiltonian terms on a cube. So the degrees of freedom are on the surfaces. And over cube, there are 6 surfaces, so it's a product of 6x. And then there are these 4-body z term around an edge. So take all the z's around a single edge and make a 4-body term. So put all these terms together, we get the 3+1D Toric code, which is a simple stabilizer code, and we always thought we understood everything. What else can we not know about stabilizer models, right? For example, we know that we can make point excitations like this. You can just do z, 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 and then we would end up with one excitation at each end of this string operator. So this is the way to make the point excitation, the gauge charge excitation in Toric code. And then we can also make a loop excitation just by applying x, 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 x over the plaquettes on a membrane. And then we make a loop excitation on the outside of the membrane. So yeah, so this is all very simple and very well understood. And then, of course, people also knew better than that, that in 3+1D, Toric code is a very simple example, and it's sometimes too simple because it doesn't embody all possible statistics that can happen. In particular, in 3+1D, we know that there can be something called the loop braiding, that if we just have loops, we can also make them braid in non-trivial way. But to see that happen, we need 3 loops. We need a gamma loop, and then we need an alpha loop and beta loop that's both linked with the base loop. And when that happens, we can exchange or braid the alpha loop around the beta loop while keeping the gamma loop there. The gamma loop is not moving. And we're just moving alpha loop around beta loop. And that will give us the so-called three-loop braiding that's discussed in all these papers. And that process can give us non-trivial statistics when we have something slightly more complicated than just toric code. Toric code doesn't do anything non-trivial if we do that. But for something more complicated, we can have non-trivial statistics coming out of this three-loop braiding process. Okay. So that's pretty much what we understand, although then mathematically there's a lot of literature, and people talk about the so-called higher category theory. So then I try to think, oh, what is that, and why do we really need to talk about it, right? If it's just stabilizer model and we understand everything in terms of sigma x and sigma z, why do we really need to talk about higher categories and all these sophisticated notations associated with that? So in particular, one thing I was trying to understand has to do with this cat, and it's what people call the Cheshire string. So it turns out that when people try to formulate a higher category theory to describe even the simple toric code, there's a necessity of involving something called the Cheshire string even at the most fundamental level. So that was one question mark I had in my head. Why do we even need to talk about this? And how does it help? And how do we really think about it in the usual sense of how we think about gauge charge and gauge flux? Okay. So let me first tell you what this is, and then try to tell you my effort to try to understand why we need to do it and how we should be thinking about it. Okay, so the Cheshire string is a type of defect or excitation inside, let's just say, the usual toric code. So we still have the same bulk excitation with the cube term and the four-body edge term. So the bulk Hamiltonian is still the same. But then we pick out a region to change the Hamiltonian to something different, in a sense to make a defect out of it. Or another way to say is that we can still refer to the original defect, then what's happening is that we're just making excitations on top of the ground state. Okay, but usually when people talk about these defects, the usual starting point is that, okay, we start from a Hamiltonian, but then we change the Hamiltonian somewhere inside the bulk and make a defect. So let's see how we want to change the Hamiltonian. So we know that if we apply this kind of plaquette Z operator, so if we just apply a single Z here, we're going to create a pair of charge, right? So that's what this Z operator does. And if we keep doing that, we can move the charge to a different location. So these little piece of Z operator, this string operator, allow us to create pair of charge and also hop them around. So this is the string operator for the charge. So the proposal for making the defect is to say, okay, let's add these terms as the Hamiltonian, to the Hamiltonian of the model. So just add this little piece of string operator, which is just a single Z, to the Hamiltonian. Of course, it doesn't commute with some of the original Hamiltonian, and then the idea is that we either throw those terms away, or we just make this term very, very big. So eventually, we throw away the cube terms that don't commute with this term. Okay. So if we just have this one little piece of string operator, and then we can ask, what is the ground state? What is now the new ground state of the system? Of course, everywhere else it remains still inside the bulk state of toric code. But along the defect, because we have imposed a sigma z on this plaquette, then this plaquette need to be in the zero state, right? And if we write it in terms of the original basis of charge excitations, we see that the ground state is basically in a state of no excitation and a pair of excitation. So it's a superposition of these two different configurations, one with no excitation the other with 2 excitations. And then we can choose to do this not just at one point, but we can choose to do this along a whole one-dimensional segment. So we pick a one-dimensional region, and then we change the Hamiltonian to this little string operator everywhere along the little segment. Of course, in principle, we can do this to any region inside the bulk. But for the higher category structure, there's a reason that people want to start from the one-dimensional defects and then go down the dimension or go up the dimension from there. Okay. And these turns out to be, of course, the Cheshire string. The one-dimensional one will turn out to be a fundamental object in the so-called higher category structure. Right. So if we impose all these little strings as Hamiltonian terms on this whole one-dimensional segment, then what happens is that the wave function now becomes a bigger superposition. It becomes a superposition of no excitations, a pair of excitations here, a pair of excitations here, and a pair of excitations separated far away, and the 4 excitations, and basically all possible even number of excitations in any kind of spatial configuration. And this is what we call a charge condensate, basically. If you have a superposition of all possible configurations of charge, the charge is condensed. And in particular, if we bring another charge from the bulk into this condensed region, then it disappears. So that's why people use this name of Cheshire. The Cheshire is a cat that's somehow there, but somehow not there. If you look at it, it disappears. So that's why it's somehow related to this phenomena, which is actually less mysterious. We have a charge condensate, and if you throw another charge inside, it disappears. Although in this particular case of gauge charge condensation, there's a total parity conservation for the gauge charge because, for example, here we only have even number of charge configurations. And if we add a charge, we'll have odd charge configuration. So that's a different state, but it's a different state only globally. It's a different state that you cannot tell from any local measurement. So in that sense, it's a degenerate state. So it's a global degeneracy. Okay. Right. Okay. So this is what Cheshire string is. It's basically a condensation of anyons or of gauge charges, and when the gauge charge is condensed, another way of saying it is that the gauge symmetry is Higgs. There's a equivalently, a symmetry breaking going on for the Z2 symmetry group. And adding a gauge charge does not create a local excitation anymore. It just toggles between the 2 degenerate ground states.
So this is Higgs, and there's a remaining unbroken gaugeable Z2.
Sorry, Z2 when it's Higgs, then there's nothing. It's just gone.
This, the pair, maybe, I don't know what the charge assignment is. This one breaks Z2 completely, or?
Each charge carries.
But this one pair.
Yeah, the pair. Yeah, as a single pair, it doesn't. But once the charge condenses, then yes. Once we have a whole superposition of all kinds of configurations like this, then locally you cannot tell whether you have a single charge or you have 2 charges in the whole chain.
Okay, so now with the Cooper pair condensation.
Yeah.
So there, in the Cooper pair case, we have Z2 gauge symmetry unbroken. That's the remaining.
So in superconductor, we still have a remaining Z2 symmetry. Right. In this case, I'm talking about Z2 breaking down to nothing. Yeah. In the Cooper pair condensation, we have all the Cooper pairs, and then they condense. Mm-hmm. Right. Here, it's each anion condense.
Okay.
Yeah.
Okay. Right.
Okay, right. So there's there's this degeneracy associated with whether we have total even or total odd charge on the defect. Right. So actually, even though this thing seems pretty ad hoc to talk about for toric code because we thought we understood everything about toric code, but in some other context, in some other gauge theories, Cheshire string shows up in a much more natural and necessary way. And this was already discussed in the 90s when people were thinking about non-abelian gauge theories. So when the gauge group is a non-abelian group, then actually what happens is that the gauge flux, the flux loop has to be, in a sense, a Cheshire, because the flux loop in a non-abelian gauge theory, let's say associated with a particular group element, then just because the group is non-abelian, so this group element has to break some of the gauge symmetry, unless it's in the center. But as long as it's not in the center, then it breaks some of the gauge symmetry. And when it breaks some of the gauge symmetry, then equivalently, all those charges that transform non-trivially under that part of the gauge symmetry have to condense on the loop. So this is, of course, equivalent. For example, let me give you the simplest example of just the gauge group being S3. And then we can take G to be one of the rotation operation. And then the symmetry group is broken down to, of course, just the rotation subgroup. And then all the non-trivial one-dimensional charges, there's a sign rep, if you remember, for S3 that transform non-trivially under the broken part of the group, which is the reflection part of the group. And those one-dimensional charges have to condense. So if we have flux loop that's associated with rotation, there's actually a twofold degeneracy associated with that, yes?
So what's the difference between ordinary loop excitation versus this kind of Cheshire string?
Ordinary loop, that's gauge.
Well, in Toric code, you can also have ordinary just loop excitation.
Yes.
But then this is also a loop.
Yes.
I don't think they are the same. So what's the difference?
Oh, yeah. So here for the non-abelian gauge theory, I'm still talking about gauge flux loop. I'm just saying that in non-abelian gauge theory, these gauge flux loop naturally have to also have charge condensation. For toric code, they don't have to happen at the same time. For toric code, it's abelian gauge theory. So the flux loop doesn't have to have charge condensed on it. But for the non-abelian one, we have to condense these charges on the flux loop. And this is equivalent to saying that for the flux loop, actually, we shouldn't just relate it to a single group element. We should relate it to the conjugacy class, which contains two group elements, which is actually associated with the degeneracy, and that's the same degeneracy. It's exactly the same degeneracy due to the charge condensation.
So in the Toric code, so it's not just you don't have to, you just cannot have a.
Oh yeah, we also can. So we can have a flux loop, and also in addition to that, we can condense charge on it. We can combine the two, but it's not necessary to combine the two. We can have a bare flux loop without charge condensation. Yeah, thanks for the question. Yeah, so in the non-abelian case, this is more of a necessity. So we cannot avoid talking about it, even though we're talking about the bare minimum excitations. Okay, and another situation where this is necessary is in some abelian gauge theories, but the abelian gauge theories with non-trivial three-loop braiding. So toric code doesn't have non-trivial three-loop braiding, but some other abelian gauge theory does, and it was pointed out in Dominic and Xie Chen's paper in 2017, maybe some math paper that I don't know, but I learned it from here, that in these kind of situations, some of the flux loop also have to be Cheshire. And this is because we can look at this picture. And so this is the three-loop braiding picture again, that we have a base loop, and then two other loops link on top of the base loop. And then we can imagine compressing the three-dimensional system down to two dimensions, just shrink the size of the system in the z direction, shrink it to a two-dimensional one. And when we shrink it in that way, we get a two-dimensional system with the base loop inside the plane. And effectively, what happens is that the base loop becomes the boundary of some different two-dimensional topological order. For example, in a very simple case of Z2 cross Z2 gauge theory, what happens is that the base loop is the boundary between 2D toric code and 2D double semyon. So these are two different versions of Z2 gauge theory, and the base loop is a boundary between the two. And what we know about the boundary between these two topological order is that the gauge charge, the bosonic charge in either toric code or double semyon, have to condense on it in order to have a gap boundary between them. So that's the only way to have a gap boundary between toric code and double semyon, meaning that in this three-dimensional Z2 cross Z2 gauge theory, this base loop also have to have charge condensed on it. So it has to be Cheshire in a way. Right? So in these kind of situation, Cheshire string is also like necessarily built in, even though we just want to talk about gauge charge and gauge flux loop excitations. Okay, so these are the way I try to justify why I need to think about Cheshire string, even though for toric code it's still not that necessary. Okay. Okay. So this is, of course, so coming back to toric code, what happens is that we don't, the flux loop doesn't have to be Cheshire. We can just have a flux loop without condensing the charge. But as the math people point out, that this is a very crucial element to have if we want to have a proper higher category description of the 3 plus 1D topological order. And in particular, the proposal was that just, let's say, for 3 plus 1D toric code, the higher category structure is like, as Sakura was talking about in the morning, there are objects, and then there are morphism between them, and then there's morphism between morphism. So for naive physicists like me, I'm just thinking about things, relations, and relations between relations. So that's how I understand things. And so in that context, the fundamental objects are one-dimensional excitations, so string-like excitations. And there are 4 types. The first one is, of course, trivial, just nothing. The second one is the flux loop, is the Z2 flux loop. The third one is the Cheshire string. Okay, so it's Cheshire strings raised at the top level of importance. And then we can have the composite. We can combine them and make a composite of such excitations. Okay, and then the morphism, the physics language for the morphism is domain walls between these one-dimensional objects. So we have one-dimensional objects, then we can have domain walls in between these one-dimensional objects. For example, we can have nothing. We don't have to have anything. Or the gauge charge, which used to be a fundamental object, now is demoted to the level of a morphism between one-dimensional object. It can be a morphism between just trivial to trivial, for example, or from flux loop to flux loop. Okay, so this is now how, in the higher category structure, how people think about the excitations in the toric code model. Okay. And then my question, so from someone who has always been playing with these models on a lattice, my question about Cheshire string is that it's always discussed in a very different way from how we usually talk about excitations. Usually when we talk about, let's say, anyons or point excitations, we talk about the string operator to generate a pair of anyon and to separate them and to move them and to braid them, right? And for the flux loop excitation, we talk about the membrane operator that's used to generate these that's used to generate these flux excitations that can also move them and braid them and etc. But when people talk about the Cheshire string, they talk about changing the Hamiltonian. And that's not how we usually talk about anyons. We don't usually change Hamiltonian to get an anyon. We don't usually change Hamiltonian to get a flux loop. And if I change the Hamiltonian to get a Cheshire string, and if I want to move the Cheshire string, I don't know if I should change the Hamiltonian back and just change it at a different location. How should I even think about it? And more importantly, the string operator and membrane operators associated with these charge and flux loop operator, they're very fundamental to tell me what the statistics is. I can derive basically all the data of braiding and fusion and F symbol and everything from these operators. So if I try to understand better the higher category structure, maybe it will be helpful to also try to think about Cheshire string from this unitary perspective, from the perspective of not changing the Hamiltonian, but just treat the Cheshire string as a kind of excitation on top of the ground state, and then think about how to generate these excitations using unitary transformations, and how that somehow tell me that this is a non-trivial kind of excitation, and how maybe it has some non-trivial whatever morphism among them, and maybe with other things. Okay, so that's my question and what I'm trying to do. So, right, so we can do all these with unitary operators, and their commutation gives statistics, and I want to know whether Cheshire string can also be generated with unitary operator. Yes?
This cylinder has any meaning at all?
No. Sorry, no. No.
Okay.
It's just trying to get a region to draw things. Sorry. Okay, yeah, and we actually did this, and Nat actually came up with the way to do this first with a 2+1D Toric code. For 2+1D Toric code, we don't even usually talk about Cheshire string, but we can because we can condense charge inside even a 2+1D Toric code, so we can even discuss the question already here. And this has relation to, of course, all the discussion about non-invertible defects inside these 2+1D things. So we did this in 2+1D, and then it can be very easily generalized to 3+1D. So let me show you this 2+1D version first. Okay. So in 2+1D, very nicely, we're back to two-dimensional square lattice, and the Hamiltonian is Plaquette term and the vertex term. So let me set the convention. I think I already set the convention that the Plaquette excitation are charge excitation, and the vertex excitation are flux excitation. I'm just picking this convention. Okay. And then in order to create a pair of charge, I apply sigma z here. Just create a pair of charge. And then that enforces that edge to be in a zero state, in the ground state. Okay. And if I have a Cheshire string, I would enforce all these dashed edges to be in the zero state. That would be my Cheshire string, and the corresponding Hamiltonian would just be z over each of these edge. And if I try to write down the wave function in the original charge excitation basis, it will be a superposition of no charge, too far away charge, 4 charge, etc. All the even charge configurations. So the question becomes how to generate such a defect starting from the Toric code ground state. Okay, but we're starting from the Toric code ground state. Everything is the topological state already. And then somehow we want to open up a defect line such that along the defect line, these qubits become decoupled into the zero state. And from that process, we hope to learn, in a way, why this is a non-trivial defect, in a sense. Okay. And this we knew how to do because we wrote a previous paper, remember, that we were trying to map between different gap phases. And the circuit to generate the Cheshire string is very closely related to the circuit that we used to map from a paramagnetic state to a symmetry breaking state with global Z2 symmetry. So this is just in one dimension, one-dimensional transverse field Ising model. One is the symmetric phase, the other is the symmetry breaking phase, And in this previous paper, we talk about how to map between the two. And of course, actually, before us, people already know how to map them. So we're not the first paper to talk about this circuit. And in particular, this of course, there are different phases with global Z2 symmetry. And we want to map between the all plus state to the 0, 0, 0 plus 1, 1, 1 state. Okay, so that's the goal. And it was proven by Matt and Sergei Bravi, Frank Vastrada, many years ago, decades ago, that this can only be done with a circuit with at least linear depths. So Joanne was talking about finite depth circuit in the morning, which means that the circuit only has finite number of layers. And the linear depth circuit would have number of layers that goes with the size of the system. So this is a one-dimensional chain of size L. Then we would need at least L layers to do that. So that was proven. So yeah, and then we wrote out such a circuit. And some people already did that before. And the circuit looks like this. So the circuit has a kind of staircase structure where each box is a 2-qubit unitary. So the 2-qubit unitary is a bunch of pi/4 rotation with some poly operator, poly generator. And there's pi/4 rotation with X and pi/4 rotation with ZZ. The details doesn't matter. What I'm trying to say is that the circuit is a linear depth circuit because if you want to try to cover the whole system, there will need to be linear number of boxes and linear number of layers. But however, this is a very special type of linear depth circuit because in each layer, we're only doing one local gate. So it's far from a generic linear depth circuit. A generic circuit would act everywhere, but here it's just acting on one region. So we're acting on 1, 2, and 2, 3, and 3, 4, and then move throughout the system in a sequential way. Right? We start from the left end and then move to the right end. So this is why we call this type of circuit a kind of sequential quantum circuit. Okay, so here's some details of why the circuit works. You can work it out, some tricks with poly operators. But what happens is that at least inside the bulk of the system, the X operator maps to the ZZ, and the ZZ operator maps to the X. So you kind of generate the Kramer-Wagner duality for the system. And this sequential structure leads to the term that this is a sequential linear depth circuit. Okay, and of course, this will also be the kind of circuit that we use to generate the Cheshire defect. Okay. Right, and how do we just start from this circuit? How do we massage it and turn it into a circuit for generating the Cheshire defect? And the observation is very simple because this story is basically the same story of mapping symmetric state to symmetry breaking state, but coupled to gauge field, right? So if we think of Toric code as just a two-dimensional paramagnet coupled to gauge field, then the Cheshire string is just a one-dimensional symmetry breaking defect on top of that symmetric background. So we can just start from a two-dimensional paramagnet and then induce symmetry breaking on one of the lines, and then couple the whole thing to the Z2 gauge field. Then equivalently, we would be having a Cheshire string inside a two-dimensional Toric code. Okay. So with that understanding, we can just take the circuit on the previous page and then turn it into a circuit in the two-dimensional Toric code. And so originally we had a rotation with X. Here we replace that X with AP because X was measuring the charge in that case, and here AP is measuring the charge. And originally we had a ZZ, but now the ZZ is replaced by a single Z because a single Z is generating a pair of charge. So this is just some operator correspondence before and after gauging. So very easily, once we have a circuit, in the previous case, we can turn it into a circuit. In this case, for generating the Cheshire string inside a two-dimensional Toric code. And the crucial thing is that we still have to do it in a sequential way. So we have to apply the gate set one by one from left-hand side to the right-hand side. And then step by step, we can generate this defect. Because these gate sets, they don't commute with each other, so there's no way we can apply them at the same time. So we have to apply one step at a time. And this is the sequential linear depth circuit. Okay, and we can check that this actually works because if you keep track of how the operators evolve, the Plaquette operator gets mapped to Z, and this is exactly how we want to change the Hamiltonian, right? We want to throw away the Plaquette operator and put in the Z as the Hamiltonian term. So this exactly does that. But the total charge remains invariant. The total charge around the whole thing, that remains invariant. So that's still a good quantity, although it's a global quantity. And now we can see that if we now tunnel a charge into the defect, it only changes the total charge, which is not observable locally, but just give us the twofold global degeneracy of the defect. Yes?
So the fusion rule of Cheshire string is that if you fuse Cheshire string with itself, you produce...
that comes later. Yes.
Can you reproduce like using this unitary?
Yeah. I'm coming to... Yes, very good. Yeah, that's something I'm talking about in a second. How am I doing? When did I start? Oh, 2:30. Okay. 7 plus question time. Okay. Right. Okay, so the first take-home message is that the generation of Cheshire string requires a sequential linear depth circuit and linear in the length of the string. So this is a way for us to see that this Cheshire string is actually a non-trivial kind of defect, because anything trivial would be something that's generated by a finite depth circuit. So anything that can be done with a finite depth circuit, I would consider it to be something trivial. But sequential circuit has a power beyond finite depth circuit. And because Cheshire string can only be generated with a sequential circuit, so Cheshire string is a non-trivial kind of defect. On the other hand, the finite depth circuit also play a very, very important role in the whole discussion of this defect, because as I said, I consider anything generated by finite depth circuit to be trivial. Another way of saying it is that if I have a defect already and I apply a finite depth circuit, that gives me an equivalent defect. So that finite depth circuit defines equivalence class of one-dimensional defect. And we use that to show that we can move the Cheshire string around and also fuse multiple defects using finite depth circuit, because those should be equivalence class of the same defect. Okay. So in particular here, if we already have a Cheshire string like this, and I want to, let's say, make it thicker, just thicker like that, I can use the same gate set, but now they're all parallel to each other. And when they're parallel to each other, all these gate sets commute with each other. So we can apply them in the same step. So this is actually a one-step circuit. So with a finite depth circuit, we can go from a very thin defect to a thicker defect. And then, of course, we can make it thinner again by applying another layer of one-depth circuit. And then if we combine these two steps, we're effectively moving the defect by one lattice constant. So movement of the defect can be achieved through a finite depth circuit. So this is take-home message 2, that deformation and the movement of Cheshire string requires only finite depth quantum circuit. Okay, and then we can talk about fusion. So fusion, so here is if we have two Cheshire strings and we want to fuse them, So fusion means that you put two things together, they should look effectively like the third thing. So that's an equivalence relation. So we expect fusion to also be realized by finite depth circuit. And that's indeed what we found. We can apply these gate sets, which commute with each other, and then effectively decouple the middle line from everything else. So the middle line is decoupled, even though the middle line still has a ZZ coupling on top of itself. Okay, so because of the ZZ coupling, there are two degenerate states on the decoupled state. So it can be all 0, or it can be all 1, while the remaining state is just a single Cheshire defect. So because of that, we can write the fusion rule in a very sloppy way. I'll talk about the non-sloppy way in a minute, but we can write it as C times C equals 2C, where the 2 accounts for the middle decoupled line having two degenerate ground states. Okay, and actually a better way of writing this is to say that the coefficient is not just a number. The coefficient is a 1 plus 1D Z2 gauge theory. So this is, of course, already discussed in these papers, this fusion rule. Okay, so through lattice model and with explicit finite depth circuit, we see how this fusion rule is realized. Okay. So yeah, fusion of Cheshire string requires a finite depth quantum circuit. Okay. And then all these discussion can be very easily generalized to 3+1 Toric code, which is something we started wanting to understand. And all the operations remain very similar. For example, if we try to create a Cheshire string from C0 to Cn, we can apply gate set like this, where the AC is the cube operator of all x that measures the charge, and the Zp is a single Z acting on the plaquette that creates a pair of charge. So it's just exactly the same circuit, and we just apply it step by step, and then we can generate the Cheshire string in a sequential way. And then once it's generated, we can make it thicker and thinner again, and eventually we can combine the two steps and realize a movement of the Cheshire string. So it's all the same thing. So Cheshire string 3+1 Toric code can also be generated with a sequential linear depth circuit, and also moved and deformed with a finite depth circuit, and also fused with a finite depth circuit. So here, very similarly, instead of writing a 2, I should write 1 plus 1 dz2 gauge theory as the coefficient, even though it's just some totally decoupled theory from the bulk. Okay, that's what the coefficient means. Okay. All right. So, and in our paper, other than this one type of defect, this Cheshire string defect, we also talk about all the other kinds of defect, because, for example, in 2+1 Toric code, it was already realized that there are actually 6 types of defects, not just one. There are 6 different types of defects that we can construct just like that. Some of them are condensates, some are not. But in any case, these non-trivial defects, what we find is that all of them can be generated with sequential linear depth circuit, and then their fusion, this is a big fusion table that I took out of this paper, all of these fusion can be realized with finite depth circuit. All right. Okay, so yeah. So this gives us a way to put Cheshire string and all these defects in the same context as anyons and flux loops and all the original elementary excitations that we talk about for topological phases, because now we can use a unitary language to talk about them, right? So originally when we talk about abelian anyons, we know that they need to be generated with one-dimensional string operator. But for abelian anyons, the string operator is very nice because we can generate it just in one step. We can use a finite depth 1D circuit to generate 2 anyons separated very far away from each other. And And then once the anyons are generated, the equivalence relation among them are just given by zero-dimensional local unitary. That's basically the definition of superselection sector for anyons. If anything that's equivalent up to zero-dimensional local unitary, they're considered equivalent. Okay? And for non-abelian anyon, the equivalence class is the same, given by zero-dimensional local unitary, but the generation cannot be done in one step. For non-abelian anyon, we have to take them one step at a time to make sure that they fuse back into the right thing. So we need to do step by step, and this basically is a sequential linear depth circuit. So we need to use a sequential linear depth circuit to generate a pair of non-abelian anyon. And then when we talk about flux loop, it's very similar. That they are generated by, for the abelian one, they're generated by finite depth 2D circuit, and then the equivalence is given by finite depth 1D circuit, and then the non-abelian flux loop are generated by sequential linear depth 2D circuit, and the equivalence is given by finite depth 1D circuit. Okay, so of course, the interesting thing is that for anyons, for point excitations, the notion of locality is very simple. It's either 0D local or not 0D local, right? If it's not 0D local, it better be some 1D thing. But starting from 1D defects, the notion of locality becomes more nuanced, because we can have finite depth 1D circuit, and then we can have higher dimensional circuit. But in between them, we also see that there's an intermediate level that's given by sequential circuit that actually goes beyond finite depth circuit, but it's not higher dimensional circuit yet. Okay, and that's why we have these defects that originally we weren't thinking about. But because they're generated with sequential circuit, so they also become non-trivial things. In particular, if we're thinking about the Cheshire string, which is a type of non-invertible descendant defect. So let me explain the terminology a little bit. Non-invertible meaning that because C times C is equal to 2C, it's not equal to identity. So this is called, so they don't have an inverse. So these Cheshire strings are called non-invertible defects. And descendant because it's basically a wave function made of the charge excitation. So this is called a descendant defect. And for these non-invertible descendant defect, they are generated with sequential linear depth 1D circuit. That's the thing I showed you. And their equivalence is given by finite depth 1D circuit. And then for some other kind of defects that's associated actually with some invertible defect, for example, some SPT defect, or in fermion system, we can have Majorana defects. Those kind of defects, if you try to generate it also in 1D, it has to be a sequential circuit as well, but it can also be generated just with a finite depth 2D circuit. And their equivalence class is also given by finite depth 1D circuit. Okay, okay, so now I'm out of time, but, and then still have more things to say. So that's about 1D defect. And then according to the higher category structure, then we need to talk about domain walls, their morphisms. And the morphisms is actually simple again because they're back to zero dimension, right? We're talking about zero-dimensional objects on top of one-dimensional things. And their generation and equivalence are back to what we had for, let's say, anyons. Their equivalence is given by zero-dimensional local unitary, and then generation is given by one-dimensional finite depth or sequential circuit, with one-dimensional circuit. So that gives us a rule to play with, because it's only because I don't understand math. So I'm trying to come up with a rule of game so that I can say for myself why I need to think about this, what I consider to be equivalent, what I consider to be non-trivial, what I consider to be interesting. So this is my set of rule, that if you have 1D defect generated with sequential circuit, that's interesting. If you have domain walls that cannot be generated locally, I consider that as interesting. If I have two domain walls, but I have ways to connect them with local unitary, I consider them to be equivalent. So with that, there are just some simple examples of domain walls we can have. For example, anyons are domain walls on trivial defect. And gauge charge, you cannot generate one gauge charge locally. Even on a flux loop, you cannot do that. So gauge charge is a non-trivial defect on a flux loop. And gauge charge is a non-trivial defect on SPD defect. And flux loop link on a Cheshire string is a non-trivial domain wall. And flux loop link on flux loop is a non-trivial domain wall. So yeah, we'll try to explain all that. So to summarize, we developed this whole idea of sequential circuit, and it turns out to be a very useful tool when we try to think about things that's gapped, or at least when we try to change gapped features in a system. So in one dimension, the sequential circuit, of course, you can move from left to right, and then in two dimension, there can be different patterns, like patch by patch or strip by strip, and then it involves some sequential application of local unitary or finite depth circuit. And in general, there's linear depths, but it's far from a generic linear depth circuit because each local degree of freedom is only acted upon by a finite number of gates. That's the general feature that we require for these sequential circuit. Basically, we gave that as a definition for sequential circuit. And a consequence of that is that the sequential circuit, it's beyond finite depth circuit because it doesn't preserve locality, it doesn't preserve short-range correlation, it doesn't preserve short-range entanglement, but it does preserve entanglement area law, hence it preserves the gap of the system. So if you want to talk about mapping between gap phases or mapping between gap defects, this is the language we need to use. Okay. And so in this talk, we use sequential quantum circuit to generate descendant excitations. We see that they can be generated, they don't have to be generated as the boundary of something. They can be generated on its own. But when it's generated in its own dimension, it has to be generated in a sequential way, signaling that it's a non-trivial type of defect. And then equivalence class of d-dimensional defects are given by finite depth d-dimensional circuit, and then deformation, movement, and fusion are all realized by such finite depth circuit. Yeah, that's all I want to say. Thank you.